How's that? Tremendous. Okay, wonderful. So thank you very much for coming this evening, and thanks for the invitation. As Mike said, I've worn various hats, but with regard to the Chiltern Society, I will come on to that as we go through the talk, because that does have an impact, or HS2 has had an impact on that, which was never planned. It was something that happened by, I'd like to say accident, that's the way it goes. Okay, so we're looking at the Chiltern chalk and potential impact of HS2. What I'm going to talk to you about first is what chalk is. You know, what is chalk? We're very, very quick to make use of it. Some of you may recognize the lion from Whipsnade Zoo on the side there. Just along the escarpment from Whipsnade is a large hole in the ground. That hole in the ground is probably the largest working chalk pit in the UK, a place called Kensworth. Just to get some feel for the size of this, if you look where the arrow is just there, that is a large lorry. The wheels, the tires on that lorry are about 8 feet in diameter. So that is a very large lorry. It just is completely dwarfed by the quarry. The quarry maximum depth it's been down to is just over 60 meters deep. And I will come back to this quarry at various times during the talk, showing some examples of some of the geology that we've seen in there, because it's quite a remarkable section. It's not easy to get into nowadays, but I mean, fortunately, I've been going in there for about the last 40 years. So what is chalk? What goes into a lump of chalk? Chalk is a biogenic rock. It's composed of the skeletal remains of a whole load of different animals and some plants. And it's the plants which are also critical. So we have things like bivalve mollusks down here, a thing called Inoceramus, bryozoan fossils. We have sea urchins, echinoderms, things like conulus and micrastas, little microfossils like the ostracods, brachiopods, sponges. That's an oddball sponge. If anybody knows it, it's a thing called Porosphera globularis. Porosphera is oddball because most sponges, and I'll mention this later, their skeletons are made of silica. Porosphera isn't, it's actually calcareous, just to make life difficult. But it does contribute to we find them in the chalk. We then find loads of microfossils, things like foraminifera, and those were the things that I spent my career, my research working on, foraminifera. So they get a mention as we go through. And then the other critical bits and pieces are these things, which are coccoliths. Coccoliths are single-celled plants, they're single-celled algae. They are incredibly important, and we'll look at those in a bit more detail. So that all goes in to a lump of chalk and gets mixed in. We also find big fossils. I put that one in just for anybody who likes the occasional ammonite. Should you go to Brighton, this is down on the beach just behind the marina. Okay, it's probably still there. It's not the easiest thing to remove. Hopefully it's still sitting there. It's been there for decades and it shouldn't really be removed. But that's a big parapozosia, which you find in the chalk in the right places. So we find big things like that. And if I was to say to you, what does a chalk cliff look like? This is probably what you would have in mind. This is the section at Beachy Head, just outside Eastbourne, and it's about 300 feet, just over 100 meters down there. There's an idiot in a bright yellow jacket there, that's me. Fortunately, there's a bigger idiot standing to my right between me and the cliff edge. That's a colleague of mine, Liam Gallagher. Liam has, whereas I worked on foraminifera, Liam worked on those little coccoliths. So the two of us have worked together for the last 30 plus years, trying to calibrate our results and make sense. So that's what you think of when you look at it. Doesn't always look like that, but that's, if you like, a classic chalk cliff. And that was formed during the late Cretaceous. So what was unusual about the late Cretaceous to give us that sort of deposit? First of all, where are we in Europe? If we look at the top there, that red rectangle, that's Northern Europe up there. This series of reconstructions are dated around about 90 million years ago. So about 10 million years into the late Cretaceous. A few things start to stand out straight away. There are large areas of continental shelf that are flooded. If you look at Africa, there's an open seaway right the way across Africa, all the way down East Africa, there's flooding, and most of Europe is underwater. Similarly, in North America, a huge great seaway running up the west coast with the, if you like, the early Rockies, which are being built up to the west of that. So it is unusual. We've got a global greenhouse climate. And when I say that, it was really, really hot. Sea surface temperatures. I'm sure if I say to you, has anybody here been swimming in the North Sea? And you think, yeah, there are one or two idiots who would do it. But greenhouse climate, during the late Cretaceous, the seas that we're talking about across Northern Europe were in excess of 20 to 25 degrees centigrade. And towards the end of the Cretaceous, there is evidence to suggest circulating at the Atlantic, sea surface temperatures got up to around about 36 degrees. So that was warm, okay? We had high sea levels. So we've got major flooding of the continental shelves. Note, there are no polar ice caps, okay? So global temperatures were really high, so we're not seeing any permanent ice at the poles. There is some evidence creeping in that there were occasional ephemeral patches of ice at both poles, but nothing permanent at all. Because the continental shelves are flooded, we're seeing less erosion and we're seeing less, if you like, terrigenous sediment, all the coarse clastics, the sands and the clays coming into the sea and ocean areas. So that's why we end up with a pure white limestone. There's very little sediment getting into it. And we also have clear seawater. I put in here, it's got a low magnesium to calcium ratio. I'm no chemist, but this, basically the seawaters around the globe have changed through geological time. Sometimes they're high calcium, sometimes they're low calcium. During the late Cretaceous, it was low magnesium, high calcium. Perhaps that's one of the reasons we have calcium carbonate coming in. So, just to try and prove and give you some evidence to what I've been saying. This is a paper from a paper published late last year by a Dutch guy and a whole team of specialists working together. A guy called Dewey van der Meer.
Traditional natural materials,
and what I want to look at the top graph is sea level through time. This is through geological time, right the way back to 550 million years. So we're going right the way back into the Cambrian. The bit we're interested in is the late Cretaceous. Let's just show where that is. That's our bit. Now, if we follow that graph that Dewey's come up with and look at the bit that we're interested in, it's effectively as high as sea level has ever been since the beginning of the Cambrian. So over the last 550 million years, at this stage, sea level was up around over 200 meters higher than present day sea level. And this has been based on a huge amount of research. Similarly, if we look at sea surface temperature through time, we're looking at the same period from 550 million years coming through to the present day. There is the late Cretaceous in that red box. We're looking at a peak there up around about between 25, 28 degrees centigrade in sea surface temperatures globally. This is a global average. So we're seeing high sea levels, very high temperatures. So that is the situation that we had throughout virtually all of the late Cretaceous. Now that has an impact because those conditions facilitated the growth of those little algae, the coccolithophorids that I mentioned right at the beginning. As I say, these are single-celled algae, and they produce calcium carbonate plates, like little limestone or calcite plates, which they surround the cell, the algal cell. People are not sure why they actually do this. It's something we still don't really know. There are various ideas, one being possible protection, which is a bit slim because they get grazed on by all manner of things. The other suggestion, which is really a bit almost too scientific, is the fact that the calcite would have refracted sunlight into the cell. And the refraction of the sunlight going into the cell, because these things are plants, they're photosynthesizing. So having that sunlight concentrated into the center of the cocosphere is probably a good thing. When they die, these plates break apart. We end up with a sediment which is made up of a mush of plates. It isn't quite that simple, because if you were to take a little cocosphere with all those plates in the top of the ocean and let it die, fall apart, and settle to the sea floor, because of the dissolution of calcium carbonate in deep water, by the time it got to the seabed, it would have dissolved, and we wouldn't have any chalk at all. So somehow we've got to get these things from the sea surface down onto the seabed without dissolving. And back in the mid-70s, a guy called Honjo was looking at this, puzzling over it, and he came up with a brilliant idea. And we've been living with it ever since. Basically, if you look at blooms of these coccolithophorids, they get grazed upon by millions of little shrimps, little things called krill, or copepods. You'll know krill, whales go around and eating them. Well, in the food cycle, copepods graze on these things. And inevitably, having grazed on the plant that was inside them, they're left with all the hard bits, and those have got to come out somewhere. So the krill poo, we end up with fecal pellets, and those fecal pellets, because they're actually concentrations of these things, sink to the sea floor so fast. So in fact, the chalk with a whole load of shrimp poo, basically. It's as simple as that. Okay, it gets more complicated, but we won't go there. Right, so let's have a look at that. I put this in, always put this in just to tempt people to say, anybody recognize where it is? It's not easy. I know it's on Earth. It's actually right up on the northeast corner of Canada. So we're looking at Newfoundland and Labrador. And this is where the Gulf Stream's coming through. Gulf Stream's warm. This is modern day ocean, so we've got a bloom of calcareous nanoplankton, coccolithophores, living in the surface in the Atlantic Ocean. A bit closer to home, okay, Cornwall, the same thing, same sort of, that is a bloom of a single species of coccolith. It's a thing called Emiliana huxleyi. It is probably the most common organism on the planet. And these things, when they bloom, they literally just form huge clouds within the seas. So that's in the present day temperatures, the present day coast off Cornwall and Devon. Imagine what it was like when sea surface temperatures were probably 3 to 4 times higher. These things really did bloom big scale. So chalk is initially a coccolith and a foramen ooze. There's huxleyi. This thing breaks down into plates. All those plates, when they've been pooed from all the shrimps, get together, and we end up with a mush, which eventually will become chalk. Because these plates are extremely small, and we're talking, okay, it's one of those things that's difficult to get your head around. They're normally between 5 and 30 microns. And a micron, I always get this wrong, is 1/100 of a millimeter. Yeah. So they are extremely tiny. You need a large microscope to be able to see them. But of course, the pore spaces between them are extremely small as well, because the fragments are small. Then when they form a rock, the porosity in the rock is extremely small. This is incredibly important when it comes to our water supplies from the chalk, because chalk streams tend to be very pure water because they've been filtered through this stuff before they come to the surface. And because the porosity is what we call microporosity in the UK, porosities even up to something like 35% is pore space, but it's very, very small. And because it's tightly packed, the water doesn't flow through it very easily. What it does flow through are the fractures in the rock itself, and we'll come onto that as we go along. There you go. That we've produced or got into we produced a sediment which we call chalk. So what does it look like under London? This is just to give you some feel. We're at Chiltern Hills. We're going to be looking at the two green layers there. I have to apologize this for. I don't see why I should apologize for it. We used to split the chalk up into 3 units: the lower, the middle, the upper. Back in 1997, after a great deal of, I'd like to say, academic thought, but it came down to almost fisticuffs, we ended up splitting the chalk into 2 units, one called the white chalk, the other one the grey chalk, which is the bottom bits there. Basically, it doesn't really matter that much, but the chalk goes underneath the Chilterns, a nice low dip. Underneath London itself, there's a bit of structure. Those of you who know geology, that's the Variscan front coming through. And then it swings up into the North Downs on the other side of the London Basin. I'm not going to go into loads of stratigraphy, just to highlight that anything above around about 85 million years. So chalk deposition continued till around about 66 million years. So anything between 85 to 66 million years, if it was deposited, it's now gone. We don't have that chalk. We don't have it in southern England. We don't have it in the Chilterns. What we're looking at, so there's no chalk younger than that London Basin. What we are interested in is this section through here. You'll see the various formation names on it. I will be referring to the Lewis nodular chalk, the New Pit chalk, and we'll even get down into the Hollywell chalk. These formations were defined back in the early 80s by a character called Rory Mortimer, who spent his PhD and a large number of years working his way through the chalk. And the scheme was eventually adopted by the Geological Survey. And since 1997, well, actually since 1987, the survey have been using it, but it became ubiquitous, if you like, from around about 1997. So that's the bit that we're going to be looking at. For those people who like old speak, it's effectively the old middle chalk. And just so that if you feel more comfortable with that. So let's have a look at it. This is the Western Tunnel on the Baldock bypass. The A505 runs from the A1 at Baldock through to Royston, heading towards Cambridge. And back in 2008, this was a glorious sunny day in August. It had taken 2 years plus to get to this stage. And I turned up on the site back in early 2006. I had no authority whatsoever. I just trespassed onto the site and said, can I come and look at your chalk? And over the next 2 years, they got so used to me that by the time we got to August 2008, I got invited to go to the official opening. So it was great fun. The Lord Lieutenant of the county, things like that. But what was really useful, if we take that, let's strip that rock, that hillside back. It took 2 years for various reasons. One, unexploded German bombs, badgers, Saxon burials, various reasons for taking 2 years. But if we strip it back without the tunnels, it meant that we had a nice continuous sequence through the Chiltern escarpment. And I was able to log the chalk really closely through this. So just to pick up 1 or 2 features, that heading off, that white strip there is heading off towards Cambridge. Yeah, you can see it running all the way through there. So this was the section that I'd been successfully able to work my way down over 2 years. And if you look at some of the chalk in detail, there's a couple of things that stand out. One, it's got all this iron staining in it, which is a bit odd. And the other thing I'd point out, there's no flints in this bit. So we've got to come back to why we get flints and why we don't get flints in certain bits of chalk. But if I say to you that these orange-brown stain bits, they're the remnants of sponges. All the skeleton, all the siliceous skeletons of those sponges have been dissolved. And that silica went into the formation waters when the chalk was still soft. And that silica from those sponges is what would eventually make flints, okay? Because there was free silica around. Well, that's good. Can we get rid of that? Yeah, good. So we'll come back onto that. So these are sort of, if you like, the remains of sponges. They don't look very pleasant, but nevertheless, they are important. Let's see where that's now decided it's not going to go. That is good. Why is it doing this to me? Let's see if that's got it going again. Yeah. Okay, you do get occasional flints. Okay. I'm not going to try and be controversial about the formation of flints. Basically, most flints that we see are following some form of bioturbation. There would have been some sort of organic activity where that flint is formed. So when we see a long sort of flint band, there's probably being a sort of still standing sedimentation, which has allowed burrowing to take place, and the burrows have eventually been replaced with silica, forming flint nodules. Just to try and prove this to you, I'm going to show you a few examples. No, it's still not doing that. That's great. I don't know this machine, so this is not good. Anybody know can help on this? Because it's not going forward. Can you help on this? Is it best to close it and then reopen? Okay. Right. So these are flints. And you can see that these have got a definite form to them. They're actually following feeding traces. We're not sure what the organism was. In some cases, things like this, which is a thing called the zoophycos flint. And you can see that when you get zoophycos, although what the flint is left with is this sort of peculiar misshapen spiral in the middle, you can see that if you look at the chalk really closely when you've got this, you find these traces. A lot of this work was done by a guy called Richard Bromley. Richard was a great guy. He was born in Hertfordshire, loved the chalk, worked on it for years, and eventually ended up as curator of the Natural History Museum in Copenhagen. And one of his tricks, this is a couple of other, these are some of Richard's photographs. I put these in. I think it's great. He used to take blocks of chalk, about cubic meter, and then he would dissolve the whole lot in hydrochloric acid. And what he would be left with were all these branching structures in the chalk, in the flints. So what he was seeing was what we call nowadays thalassinoides burrows. Again, we're not sure what produced the burrows, but you can see the branching nature. And these were, again, feeding traces, feeding burrows. There are some other flints. There's one called the Bridgewick flint, where you can actually see scratch marks. The crustacean scratch marks are still preserved inside the flints, and these are tubular flints. So most flints have an organic biogenic origin. The other thing we see in the chalk, particularly in the Chilterns, is if you look very closely, we've got this nice creamy chalk, but we've got these brown stained units. Some are slightly green up here. The green is glauconite, the iron mineral. The brown staining is calcium phosphate. This is early mineralization in the chalk. The chalk rock is a series, if you like, of almost fossilized sea floors. If I go forward, basically the fauna that you see in the chalk rock, it's really an intense fauna, loads of stuff in there. We find ammonites, we find bivalves, we find individual sponges, but we also find masses of burrows. This is typical of chalk rock, and this is key to the formation of the Chiltern Escarpment. If you want to know what the chalk rock looks like, this is it. Have a look at it afterwards. Most of you, when you hit chalk with a hammer, it's nice and soft. It's what we call putty chalk. The chalk rock is not that. The chalk rock is what it says on the can. It's really very, very hard. These came out of a couple of HS2 boreholes, in actual fact. So we know that they've gone through the chalk rock in places. Okay, you get ammonites out of it as well. This is the top end of the chalk rock, and the top rock section in Reed Quarry, which is right up in North Hertfordshire. That's the top rock sequence there. This is down, those of you, I'm sure you know it, the M40 Aston Rowan cutting section. This is nice black and white photos. This was photographs taken by Richard Bromley. The chalk rock is exposed in the section at Aston Rowan. And what Richard did was to correlate. He did his PhD was on the chalk rock, but he correlated. There's Aston Rowan, so the M40 section is there, and he correlated and looked at it right the way through the Chilterns. That section that I showed you at Reed is there. What fascinates me with the fact that in some places the chalk rock is less than ½ a meter thick. In other places, the same succession thickens up, and it can be 2 or 5 meters thick. That suggests to me potential movement on the seafloor. There were tectonics going on during the deposition of the chalk. Okay, that's a whole different lecture. We can come back to that another time. But this is one of the, if you like, main lines of evidence for that. So there's the chalk rock. It sits right at the top of the escarpment, and typical Chiltern succession. And there's just an illustration of what I've just shown you, just in detail. There's Aston Rowan, and as we go into the Great Missenden section down the Misbourne Valley, we find this section thickening up. And I put this in basically to show that, because if we go, the chalk rock is effectively just in the top of the escarpment. It's one of the reasons that the escarpment is still there. It's so hard, it does not erode very easily. We're looking at a long history in terms of the presence of the Chiltern Escarpment, and that in itself is another study. But basically, the crown of the escarpment is formed of that rock that we have there, the chalk rock. Here, this is again the book. There. I'm just going to take you a bit lower down when we come down here, because you can see There's a sort of dark, well, grayish layer in there. These are marl seams, clay-rich seams. They become increasingly more common as we go down through what was the middle chalk. This again is highly significant. I said to you before, there's no flint in it. If you get lots of marl seams, when the silica was free silica ions circulating in the sediment, if there was clay present, that silica got stuck. It adhered to the clay minerals and got stuck there. It couldn't form flints. So where we've got lots of clays coming through the what we call the middle chalk, or this new pit formation, then we don't get flints, very rarely. And here's a couple of the clay bands running through here. Now, I said to you right at the very beginning, very little terrigenous sediment going into the chalk seas. We're not seeing an input. We do get some clays, but it didn't come from erosion of the surrounding sediments. It came from volcanogenic directions. Most of the clays, not all, but most of the clays that we find in the chalk originate in spreading oceanic ridges. So those clays there, running along there, some of these can get up to about 10 centimeters thick. So they can be quite substantial. And that impacts on water flow through the chalk. So that's the new pit. The new pit chalk typically is clay rich. Now I put this in just to show you at the time when that chalk would have been formed, we had the Atlantic Ocean really beginning to spread fairly rapidly. And you got volcanic activity down the mid-ocean ridge. Just like we had from Iceland, and we get from Iceland on a regular basis, but certainly back in 2010, I remember it very well because I was stuck in South Africa, and the planes wouldn't fly because of the circulation of the volcanic ash. And where was it all going? It was all going, following normal sort of Coriolis forces, following the wind directions coming across into northwestern Europe. And those clays that I've just been showing you from the new pit chalk in the Chilterns, if we look at the trace element geochemistry of those clays, and this has been done, it's been done by a guy called Dave Ray down at Greenwich. He's recognized exactly the same clay seams in northwestern Germany. He can correlate individual southern England right the way across into northern Germany, because these were volcanic ash deposits during the late Cretaceous. So it gives us a fantastic control on the stratigraphy. There's a couple of clays again. This is Kensworth Quarry. This is not Baldock. You can see a couple of marl seams running through there. We're getting fractures coming in. And we're going to fractures because they are, again, an integral part of the geology that we're talking about. What are fractures? Fractures occur in the chalk all the time. They're natural fractures. This looks like a pretty cruddy section of chalk at the top of Kensworth Quarry. But just to help you, there are two marl seams running through it. And if I put these lines on it, those are all joint systems running, probably crossing each other at around about 60 degrees. And within the top parts of the new pit chalk, which is where we are, that's exactly what you expect to find. So these joint systems are incredibly important because that's where the water flows. That is our aquifer. I mean, 66% of our water in southern England comes from the chalk. It doesn't come from all those really fine, tight pore spaces. It comes from these fractures. And we'll come back to that. Rory Mortimer, who defined all the formations in the first place down here, Rory, bless him, has even gone so far as to calculate the fracture frequency in each formation. So you can look at a cubic meter of chalk and work out how many fractures you would expect to see in it. Again, you think, has he got nothing better to do with his time? But it does have a useful impact. And again, I'll come back to that as we go through. Because what I'm going to do is to take you to an exercise that started back in 2008. For those people in the audience, and there are 2 or 3 who knew my father, they would know that one of his guidelines through life is never volunteer for anything. Okay, this was my mistake in 2008. My father was still alive just about, but basically I didn't listen to my father. I should have done so. I got an annual membership renewal for the Chiltern Society, which I'd been a member of for years. Chiltern Society, basically, if you're being polite, they're 6,500, 7,000 people who look after the Chilterns on a voluntary basis. If you look at it from a non-polite point of view, they're a crowd of NIMBYs who objected to the M40 in the first place, and they certainly don't like the HS2. But anyway, back in 2008, I put with my membership form, I put in, I'm a chalk geologist. Is this any use? It took them about 3 days to phone me up. And the phone call went and it said, we've got this river, which is this river flowing down here, the River Misbourne. It keeps disappearing. Can you tell us why? So I have no idea. I've never been there. I'll look. So we walked, had a couple of walks out. And if where the red arrow there is, you can see it's a sort of limey green color. That is the new pit chalk outcropping underneath the river. So that is the clay, that clay-rich chalk with all those clay seams in it. Just to prove it, if you go new pit chalk, that's what it looks like. Those clay seams. That's the one from Bordeaux. Okay, because it's got clay in it, water flows over it. It doesn't sink through it very easily. So the river past Amersham over the new pit chalk has tended to flow pretty well, even in dry years. If we come down to this bit here, the next layer of chalk, which is the layer of chalk that was sitting on top of the new pit, it's called the Lewis nodular chalk. The Lewis nodular chalk has got great big holes in it all over the place. It's fractured and water disappears through it. And I found that when I actually crossed the boundary, if you like, between the new pit chalk onto the Lewis chalk, that's what I found. That is should be a perched mill stream. The actual river disappears underground about 80 yards further upstream. So I was able to write a report for the Chiltern Society to say, here you go, that's why your river keeps disappearing. It's the chalk underneath it is completely screwed up. It took then about another 2 months. So I got a phone call from the chairman of the Chiltern Society who said, would you like to be the geological advisor to the whole society? And I said, but I thought you'd already got one. And he said, yes, we did, but he's just died. So I said, have we got a job description? He said, no, because you haven't written it yet. So I said, is it a job for life? He said, well, the other guy, yeah, okay, fine. So I am still the geological advisor to the Chiltern Society. That was 2008. It was really nice to get the job then. I had a few public inquiries, a few quarries to visit. It was very straightforward. But then in 2010, they invented HS2. We'll come on to that. Okay, so the Misbourne Valley. This is a recent publication, paper 2020. The Misbourne River on here, if I can find it, is this one. Okay, all the rivers along here, these are the rivers coming out of the Chilterns, various rivers. We've got the Gade that comes through Hemel Hempstead and the Misbourne. There's actually the Chess in here, which hasn't even shown up as a blue line. All the red spots on there are sinkholes. Those are dissolution places. They tend to be related to where there is tertiary sands and clays on top. The acid rain going through them dissolves the chalk. You get holes appearing through the chalk. So down through the Misbourne Valley, over the bit where my river was disappearing, it's actually riddled with sinkholes. It's not surprising that the river keeps disappearing. What surprised me was the fact that there's a river there at all. So that's the bit that we're looking at. Now, I'm going to come forward We've been talking about the chalk. We got up to around about 85 million years. So we got to leap forward 85 million years to just about 500,000 years ago. This is a reminder. This is what you might have seen wandering across the Chilterns at that stage. There are mammoth tusks in Aylesbury Museum and various other places. So we did get mammoths. And what we're looking at is this deposit, the pink stuff, going all the way across the map here. There's the chalk coming down underneath there and the River Misbourne. But we have this pink layer going all the way through. We're going to call it the Beaconsfield Gravels. It's a nice geological name. It's pretty cruddy. It's the stuff that's on top of the section here. This is Springfield Pit near Beaconsfield, long since backfilled, I think. And where I'm taking, this is the M1, M25 junction where myself and my wife live. It doesn't look like 450,000 years ago, what we had was an ice reached over through the Chilterns, had come down through the Vale of St. Albans. That's fine in itself, wouldn't be a big problem, except that going in the opposite direction was what was called, or what we call, the Proto-Thames. And this stuff, the pink stuff I showed you flowing through here, the Beaconsfield gravel, those are the gravel deposits that the River Thames, 500,000 years ago, was depositing. And what happened, here we go, there's a sort of, if we look at this sort of, the sort of arrows coming through here, that is the glacial front. So the glaciers are coming down, the ice sheets come right over the back of the Chilterns here, come down into the Vale of St. Albans. There's St. Albans, and there's Beaconsfield where the gravels were. And that river that was flowing up there has come up against that ice sheet and it can't get any further. There was also an ice sheet going down the Lee Valley, going down that direction as well. So let's just go. This is taken from the Beaconsfield geological map, and just to give you some idea of what it's showing. That route there, A, is the route of the original River Thames, so about 500,000 years ago. The Anglian ice period, the Anglian ice age, lasts from around about 470,000 years to 425,000 years. It blocks the river. And because it blocks the river, it starts to form a lake. It's an ice-dammed lake. When they built the M25, I was able to go into the cuttings and we found the classic glacial varve deposits. And they're underneath the junction of the M1 and the M25. That lake, it's still got all this water from the Proto-Thames coming into it, carrying loads of sediment. That started to form a delta, which started to back up. Very useful for 19th and 20th century cement makers, because that's where all the gravels for London came from. But eventually, that lake backs up and the River Thames is pushed onto a southerly route, which is the route that it now follows, okay? But originally, all those rivers that we see flowing through the Chilterns were actually tributaries of the original River Thames. And this is one of them. This is the River Misbourne. And it's not surprising, given the history of all that, sort of the fact that the chalk is fractured, it's got sinkholes through it, it's had an ice sort of sheet going over it, that it's a pretty fragile system. We're dealing with a fragile groundwater system, which is very easily damaged. And to be quite frank, that bridge is just about where the tunnel for HS2 goes straight underneath. Okay, so although there was there was minimal settlement, we're talking millimeters, when the tunnels were drilled under that section. It's certainly, it's a fragile aquifer. Which brings me on HS2. I know you were interested in HS2. I've lived with it for 13 years. Basically 2010, I'd been working for the Chiltern Society for a couple of years by then, and they sent me this map. This is the first map I had. It was produced by Buckinghamshire County Council. And if we look, we started with at least 3 alternative routes. There were actually lots more, but these were the 3 ones that they had going through Buckinghamshire. This one down the middle, that was always what was called the prime or the preferred route. We have no idea who preferred it, but it was there and it's been on the map ever since. Okay, whoever came up with that, yeah, he was worth whatever he was paid to do it. But that's the route that HS2 broadly, it's moved a little bit side to side, but it's following. So that's what we're following through. And you recognize this. This is the same valley I've been talking about, that with that river that keeps disappearing. They chose to put HS2 straight underneath the Misbourne Valley. Okay, so it's going, I'll show you as we go through. There we go. That is effectively the M25 coming through here. There is the start of the tunnel. This route has changed slightly since this was drawn, but that is broadly the route that it's following. That was the first attempt at a route for the Chiltern Tunnel. I put this in just to show how upset people can be. This is the draft environmental statement that was issued by HS2. Fortunately, it was a draft statement. Eventually, this is going to go to Parliament, to MPs, to show how much work had been done working out where HS2 was going to go through. And section 8.4, I went through the whole of this. It's I got nothing better to do. Here we go. 8.4.3, the bedrock geology of the majority of the study area comprises Cretaceous chalk. That's correct, great. The undifferentiated Cretaceous Gault and Upper Greensand Formation consists of mudstone, sandstone, and limestone. Correct, fine. This overlies the chalk and outcrops from the northern 1 kilometer of the root section. Since when has the Gault or the greensand overlain the chalk? What they've done is they got the whole section upside down. Okay, so the environmental baseline for HS2 was based on an inverted Cretaceous section. They couldn't get the geology the right way. What annoyed me most was the fact that it wasn't the fact that somebody had made a typo and hadn't spotted it. I can sympathize with that, but they'd actually copied it and pasted it through the environmental state. It got repeated. So, you know, it was up to people who got nothing to do with HS2 to point out that errors had been made. So that's what it should have looked like. And the tunnel that they're talking about is effectively running from back end of the chalk through to the Wendover area where it comes out on the Gault clay. Now, right at the very beginning, I worked very closely with geologists from the water companies. And one of the senior geologists in 2012 said to me, if you're constructing a railway on the surface, it doesn't affect your water system. It's not a problem. It's when you start putting it underground that your problems start, because you're going to have an impact on your aquifer. The main question I've always asked for the last 13 years, from when I started on this, why are we tunneling under a valley anyway? I mean, you don't put tunnels under valleys. You put tunnels under mountains, underneath English channels and places like that. Not under. We're putting a tunnel under a valley because it's going through an area of outstanding natural beauty. This is supposed to be preserved. And basically, we're not preserving it. We're putting a high-speed railway through it. So, yeah, from that point of view, it's annoying. If we look at where the tunnel is going through, just as a general scheme, if it was being put through the, if you like, the good aquifer on the top, that would be difficult to tunnel. The middle chalk, moderate aquifer, few flints, moderately easy to tunnel. The grey chalk, poor aquifer, no flints, dead easy to tunnel. Myself and the other guys from the Chiltern Society went to the House of Commons for the Select Committee. We presented a plan where they should put the tunnel down into the lower chalk. because that would be dead easy to tunnel and it wouldn't affect the aquifer. So what they did was put it straight through the top bit. And that's where it's still going. It's going straight through the main aquifer in the Chilterns. Now, just to get, so I keep going back to this map. This is the geological sheet for this area that was published in 2005. If I say to you as geologists, can you see if you can find any faults on it? You might be able to say, well, is that a fault there? That's possible, but that's probably about the only one. There are no faults on there at all, apart from that. We know that's not true because every section I've ever seen in the Chilterns has got a whole load of faults through it. In 2014, Chiltern District Council had a separate study. They funded a separate study to be carried out looking at alternative routes for HS2 going through the Misbourne Valley. You can't see them particularly clearly here. There's a green route through there. Wendover is up here. The M25 is there. So this is going from south to north. I was asked to peer review this report. And what struck me at the time when we put the cross section together was that there were a whole series of faults running through, right up over the escarpment. And when I asked the geologist about this, he said, the only way I could get the geology to fit on the regional dips that we've got is by putting faults all the way up through the Chilterns. He says, the only way you can make it work. So this is one of the first times that somebody said, actually, there's a lot more structure in the chalk than people have given credit for in the past. So high number of faults are marked in red all the way up there. Now, the BGS, for totally, well, I wouldn't say different reasons, but the BGS has been paid by the Environment Agency over the last, since around about 2015 they started. For the last 8 years, they've been systematically looking at all the river catchments up through the Chilterns, which included the Misbourne Valley, which is what this is. And this is one of the field slips that the geology team put together for the Misbourne Valley. And the first thing you see is these great big red lines going through. These are faults that they've recognized, which are based on good field evidence here or HS2 evidence on the sides there. And this is HS2 data for that one. There's also faults crossing through the bottom of the valley as well. So we're seeing a lot of structure and good evidence of fault. You can see these things that have been noted on a field slip. And it's no surprise, this is back on the Baldock bypass again, faults running through here. This was, you can see the offset there. This was when I was logging through it. You could pick out the faults. They ended up having to mesh the sections and rock bolt onto them because there was so much structure in there. So no great surprise there. And you can see it running, you can see all the mesh on the sides there. This is Kensworth Quarry again. Back in 2014, if you remember, those of you who remember what the winter was like in 2014, January, February, we had 200% plus rainfall. We ended up with a lake at Kensworth, which was probably 1 kilometer long. It was 13, the quarrymen reckoned it was about 13 meters deep in places. That's because it's sitting on the new pit chalk, which is full of clay, and it doesn't like draining away. But when the BGS came in and looked at, they recognized faults there, they recognized faults there, and these things in the field, the chalk ends up looking like a mush. It's completely disaggregated and smashed to pieces. You can see a fault running through there, but this has an impact on HS2. I'm just going to show you one example. This is part of the tunnel. It's still tunneling through here, coming through the north end. The tunneling machines haven't reached here yet. They're just about off the bottom of the screen as I speak. But what there is on here is what's called Shardlow's Lake. This is a 17th century ornamental lake that was built in the grounds of Shardlow's house, which is up on the hill here. It says here Misbourne crossing, so the tunnel will be going underneath the river Misbourne at about that point. That's Shardlows Lake. It's actually a very nice lake if you go for nice, pleasant walks in the Chilterns. And there's a lovely little coffee shop at the south end of it. That is where Shardlows is, according to the geological field slip that I showed you, smack over the top of those two major faults. If we go into the actual official HS2 cross sections, and when you dig through all the reports that they bury in places, you can actually find these things. What I'm going to show you, that Shardlows Lake is just in there. What is important in this bit is that there are two lines, red lines running down there. Those are major faults. And those are major faults that have been moving through time. And because underneath them is this dark gray layer, which is what's called structuralist chalk. It's called structuralist chalk because any structure that was originally there in the original sediment has been totally destroyed. It's gone. It's held together by bits of sediment. It's not really strong. You wouldn't want to build on it, I can assure you. Okay. And in fact, if we go through the geologists, these are some of the engineering geologist logs. They say it's structuralist chalk composed of off-white, slightly sandy, silty. I've got this in, this is a bit on one of the other boreholes. It's very fractured in places, so we know there's fractures in there. And below Shardlows Lake, two tunnel crowns will be at most 20 meters below that lake. Okay, and below that, there's a small retention. Any movement we get on that retention dam, then this lake could literally disappear downstream. So the tunnel is going through from down here, right the way up to off the top of the map there. The other thing I've just picked out where that star is a water pumping system. This is part of the public water supply. Everybody knows it. It's well established. In fact, it's one of the best sources of information about the geology in the area because we've still got the original engineers' logs from when the boreholes were drilled at the water pumping system back in, there we go, 1991. If we look at the section there, it goes down, it's 16 meters from the top surface down to there before we hit solid chalk. Above that, it is weathered up at chalk. It is extremely unstable. It would just actually fall apart if you were to take out. We know it falls apart because when they tried to drill the boreholes for the ground investigation, the gray bits were all the bits that they got no recovery whatsoever. Okay, there's a nice borehole in the middle there with lots of good recovery. Actually, it doesn't have any recovery at all. That is completely untrue. They ended up having to re-drill all the boreholes through this section because the recovery from the first boreholes were completely lost over that upper section because the chalk is so disaggregated. If you put it on, this is on detail, class are weak, medium density, wide like occasion subangular flying, coarse gravel flint, rare subangular cobbles. Basically, the chalk is so weak that its strength couldn't be measured. And this was underneath Chalfont St. Giles, where that water pumping system is. The tunnel is now, the crown of the tunnel is there. Tunnel has now been drilled under this, and it worked. Everybody was overjoyed, because the tunnel went there, and Chalfont St. Giles as a village did not disappear. That's the top of the tunnel. But that is the river through Chalfont St. Giles. It's an old photograph now. But what we're looking at here is the potential total loss of surface water from the Misbourne River and effectively the aesthetic loss from the removal of all those habitats, the riverside habitats, by removing the river and having a permanent dry valley. So there we go. That's the tunneling where we started, the South Portal. Those are the two tunneling machines which are, as we speak, heading towards Shardlows Lake. I think I'm the one in the blue helmet there because that was when I got to have a ride on the machine. And that was Florence that we got to ride on. And those are the tunnels going in there. Currently, Florence and Cecile, the two tunneling machines, are just passing west of Amersham. They should be under Shardlows Lake, May, June this year. Just to finish, if you think back to the old Have I Got News for You credits, and can you remember the bit where the train goes whizzing round the side of Chequers? Well, that's exactly what they did. They moved it to the west, so it didn't go anywhere near Chequers. So there you go. That's what we're dealing with in the Chilterns. Thank you very much for listening. And if you've got any questions, I'll do my best. Thank you.
Thank you very much. Are we working?